The global supersymmetry includes the transformation between the fermion and the boson, which is the extension of the space-time symmetry. But we can this global supersymmetry can be extended to the local supersymmetry. This is similar to the global symmetry to the local gauge symmetry. So originally the supersymmetry transformation, the delta, is given by the exponential of the Grossman variable and the supercharges, and this Grossman variable is the independence of the space-time, but we can make these parameters as a space-time dependence. Then the supersymmetry becomes the local one. Like as the local gauge symmetry, there should be the spin 1 gauge field. In the local supersymmetry, there should be the spin derivative graviton field. We can denote this derivative spin particle as a psi mu, where the psi carry the spin 1/2 and the mu index carry the spin 1 particle. So let's focus on the wider spin derivative particle is necessary. So we can consider the SUSY transformation of the scalar fields and the spinor field. For the delta pi, this is equal to the epsilon psi, because on the left hand side there's a no spinor, so the right hand side there are two Grossman number, and if the SUSY transformation acts on the scalar field, then it yields the spinor field. And the delta psi is proportional to the epsilon, because of such proportionality sort of the epsilons arises from the SUSY transformations infinitesimal expansion of this exponential. And in the left hand side there are one spinor component, so there should be the spinor component here, and for the if the SUSY transformations acts on the side, then it is the pi, and because there is spinor, so to satisfy the covariance, there is a gamma matrix. But we can generalize this global SUSY transformation, which is composed the scalar particle and the spinor particle. In the local supersymmetry version, now the epsilon is a space-time dependent, so the derivatives of the epsilon terms are added. So if we consider the kinetic term, the free particle, there's no interaction term, and assume that the pi and psi is massless for simplicity, then the kinetic term can be written like that. And if we consider the SUSY transformations of the derivatives of the scalar and spinor field, then there should be the additional terms which comes from the derivatives of the epsilon. This is a similar logic to the local gauge symmetries, and the associated spin 1 gauge field is arise. So there's derivatives of the epsilon, so we should add the additional term to makes the Lagrangian becomes invariant under the local SUSY transformation. So we can add the following term. Here all the forms are same, but instead of that we can add the spin derivative particle, where this psi mu a transforms like such a form, which contains the derivatives of the epsilon. So the transformation of the original Lagrangian and additional Lagrangian L delta, the two terms are cancelled each other, so such a spin derivative particle can explain the local supersymmetry very well. So such a spin derivative particle is called the gravitino as a superpartners of the graviton. And for the spin derivative, we can write the Lagrangians with the following form. There's canonical deltas here and the gamma matrix. Here's the spin derivative, and by using the actions principle, we can obtain the equation of the motion. Such a spin derivative is called the lateral swing of field in the regime of the quantum field theory, but in the local supersymmetry we'll call this the gravity as a superpartners of the gravity. We will apply the Biot formalism for the local supersymmetry. Such a Biot field is the adaptive to explain the coupling between the gravity, such a matrix, spin 2 particle, and other matter field like as the spin 0 scalar, spin 1/2 spinor, and spin 1 vector field. We can find the local Minkowski space-time by the equivalence principle of the general relativity theory for given matrix, and such a locally inertial coordinate on such a basis can be obtained. This is called the Biot field, and such a Biot field is roughly proportional to the root of the matrix. We can represent all the quantities in the Riemannian geometry, like the cross-polar symbol or Riemannian curvatures. We can written this quantity in terms of the Biot field. For example, the covariant derivatives of the matrix tensor is 0. By this, we can obtain the relation between the Christopher symbol and the spin connection, where the spin connection is given by the derivatives of the Biot field. So in the Biot formalism, the Christopher symbol is replaced the spin connection, and similarly, the Riemannian curvature can be written by the both derivatives of the spin connection. So the spin connection is the gauge field. And also the action can be the written by the Biot fields and the spin connections. So this is the action for the pure gravity, spin 2 part, and for the spin derivative part, this is a lateral swing field, and now the partial derivatives replaced by the covariant derivatives, which includes the spin connection, the gauge field part. So now we also need to add the SUSY transformation of the spin 2 and the spin derivative. So the SUSY transformation of the Biot field yield that the spin derivative particle, and the SUSY transformation of the spin derivative particle yield the spin 2 particle like as the Biot field. Also, we can consider the SUSY transformations of the spin connection yield the spin derivative particle. So the point is the Biot field and spin connection represent the spin 2 particle, and if we ask the SUSY transformation, that it yields the spin derivative and vice versa. This is called the supergravity Lagrangians. Most simple form, there's no interactions with the spin 2 and spin derivative with the other matter field. We can also add such a term, then we can extend it. And because there is only the one supercharge, so this is the capital R is equal to the 1. Also, we can make the coupling with the other field, like as the gravity spin 2 matrix and scalar fields with the covariant derivative, and covariant derivatives or spin connections with the spin derivative, and the gauge kinetic functions. So the gauge field and the spin 2 particle can be also coupled. So we discussed now the local supersymmetry, including the spin 2 and spin derivative, but we can also check the algebraic point. So the local supersymmetry, this can be extended step by step. In the spatial relativity theory, we know that the space-time symmetry is given by the Poincare algebra, which includes the spin operators and the momentum operator. And there is the commutator relations of this operator, and we can extend this to the super Poincare algebra for the supersymmetry. Now the supercharges are added. The supercharges roughly is given by the inverse of the Grassmann variable, and we can obtain the GT graded SUSY algebra. So the supercharges is odd generator, so the commutator relations between the Q and the Q's becomes anti-commutative. And also there's another steps that we can extend the Poincare algebra by adding the scaling, the Delaton operators, and the partial conformal transformation. This is called the conformal symmetry or conformal algebra. Also, we can consider the commutator relations, including the such as scaling operators and the SCT operator. And we can combine this SUSY algebra and the conformal algebra, which called the super conformal algebra. Now that there are many generators through the basic operators for the Poincare algebra, the spinous operator, momentum operators, and the this S now let's release the Latin field, the scaling operator S, and the SCT transformation, and the original SUSY supercharges, and there are additional Barrow-Mills operators and additional bosonic operators, which is the correspond to the SUSY version of the conformal algebra generators, and also we can consider all the commutator relation between them. So why we need to consider such a super conformal algebra? Because such a super conformal algebra is helpful to construct the gravity theory. Such a gravity theory arises naturally from the gaugings of the conformal symmetry. The gauge field connections can be defined like that: H mu, which includes the generators of the super conformal algebra. So the XA, the summation of these all generators, and there's a given commutator relation. Then we can obtain the curvatures as this curvature is the correspond to the Beer strength of the gauge theory. So there is a partial nu H mu commutator relations and structure constant, because this is similar to the non-abelian gauge theory. So now that this H mu includes all the generators of the super conformal algebra, and we can construct the gauge invariant action from this Beer strength or curvatures. So this is called the Lagrangian for the conformal supergravity, because this curvature or Beer strength contains all the generators of the super conformal algebras, and also we can add some lattice coupling because this is just a minimal construction. So from the super conformal transformation, we can obtain the supergravity by the gauge fixing, and there are some more complicated calculations, but I will skip in here. We can obtain the up and the d terms is Lagrangian similarly in the supergravity, and the effective scalar potential because there is additional scalar component, and this makes the behaviors of the Higgs and the electrosymmetric breakings are different, and especially the super Higgs effect makes the massive gravity by the Etienne Goldstein. So the point is that now we can make the supersymmetry becomes the gauge symmetry, so with the algebraic point of view by considering the conformal algebra. So now again turn to the graviton and gravity now. So we can consider the matters coupling with the graviton and gravity now. There's a Planck surplus in the coupling, and the graviton, the metric field, the coupled to the energy transfers, the matter sum, and there are the SUSY transformation. The SUSY transformation of the gravitons is a gravitinous spin derivative, and we can also consider matters background. This is similar to the original global supersymmetry, and we can consider the scalar potential in the such a local supergravity. There is a scalar potential in the exponential, and the superpotential, and the gauge kinetic function. These scalar potential and the superpotentials are surplused with the Planck scale, coupling the proportions like that. And also we can construct the multi-coupling and the SUSY breaking. So the SUSY breaking effects all the surpassed by the Planck scale. And already we discussed gravitational interactions a few videos ago. This is the gravitinal, and so in the Lagrangian system is the gravitinal here, and there are the Planck surplus coupling, so scalar particle and the superparticle, the Brownian field, and because of this spin 3/2 particle carries a mass dimension of 3/2 and the spin is a mass 3/2, and the scalar carries the partial derivative, so the volume mass dimension analysis there's a 1/the Planck scale, and similarly in the gauge fields and its superpartners, the gauge field is the Brownian mass dimension of 3/2, gravity through mass 3/2, and the field strength mass 2, so that there should be the mass inverse with the Planck scale suppression. So we discussed some very brief introductions of the super symmetries in the gauge and the locals version. We make the Grassmann numbers as a space-time dependence term, and this requires the spin derivative makes the invariance of the Lagrangians under the Sui transformation, and naturally yield the spin derivative particle, and such a spin derivative particle can be written by the Lorita-Schwinger field, and this is the superpartner of spin 2, so that we should add the gravity theory with the matrix, and this can be written by the Biot field for the matrix coupling. And in the algebraic point of view, such a supergravity can be obtained by the conformal algebra. So yeah, this is it. And in this slide we discussed some higher symmetry like as local supersymmetry, and also some extensions of the gravity, and maybe I will turn to the next times like as a brief introduction of the string theory.